If you'll recall, back in Lesson 19, we solved polynomial inequalities. We'll be doing something similar here. We'll be solving rational inequalities. The steps are quite similar, but things do get a little more complicated because of the fractions involved. Notice these steps inside this rectangle. They really do correspond to the steps that I gave you back in Lesson 19. Let's do example 1 together. The first step is to rewrite the inequality to get 0 on the right-hand side. Sound familiar? This is the same thing we did to solve polynomial inequalities. However, there's a little bit more here. It says, if necessary, turn the left-hand side into a single fraction. There's also a warning. It says, never multiply each side of an inequality by a variable. So we'll start by subtracting 2 from each side, and we get this. Now at this point, you might be tempted to multiply each side by x minus 3 to make the fraction go away. That's what we would do if this were an equation, not an inequality. But remember the warning, never multiply each side of an inequality by a variable. If we were to do that, we would completely mess up the problem and get the wrong answer. Instead, we must finish step 1, turn the left-hand side into a single fraction. That means that we need to put the 2 over 1. Then we multiply the second fraction by the form of 1, x minus 3 over x minus 3. This will allow us to subtract the fractions. The fractions have the same denominator, so we will be able to subtract, but we do have to be careful here. Remember that when you subtract 2 fractions, if the numerator of the second fraction contains more than one term, you have to distribute the minus sign to subtract all those terms. This gives us the inequality. Negative x plus 6 all over x minus 3 is less than 0. That was step 1. Now we're ready for step 2. Treat the fraction on the left-hand side as a function and determine both its domain and its set of real zeros. In step 2 of solving polynomial inequalities, we did the same thing, except we didn't have to worry about the domain of the function because the domain was all real numbers. Here, for this function, we can see that x can't be 3. That means its domain is all real numbers except for 3. As for finding the zeros of this function, we did that back in the previous lesson. Set the output y equal to 0 and solve for x. We multiply each side by x minus 3, and in doing so we need to put that x minus 3 over 1 to cancel this in this. The left-hand side is just 0, the right-hand side is negative x plus 6, so that gives me x equals 6. That's our 0. That's step 2. Now for step 3. Use the zeros to split the domain into subintervals where the rational function is either positive or negative. This is the same as step 3 of solving polynomial inequalities, except that now we're splitting the domain up into subintervals instead of all real numbers up into subintervals. So as before, I'll draw a number line. I'm going to show here that 3 is not in the domain. I'm going to put my 0, 6 on the number line. And then I've got 3 intervals. I'll write these down. This is the beginning of my interval chart. Step 4 says, for each interval, pick a test input and calculate the associated output of the fraction. In particular, note its sign. What numbers should I pick as test inputs? It doesn't really matter as long as the numbers are inside the intervals. So I'm going to pick x equals 0 for the first interval, x equals 4 for the second, and x equals 7 for the third. Now we need to compute the outputs for these inputs. So I'm going to take the x's that I've chosen and plug them back in here to calculate the associated y's. Doing so, I get these 3 numbers. Notice that I did these calculations myself, but I could have used the calculator to get the outputs if I had wanted to. Remember, the important thing is the sign of the output. This one here is negative, y is less than 0. This one is positive, y is greater than 0. And the last one is negative, y is less than 0. So we've finished step 4 and on to step 5. We're supposed to write the solution set. And here it says it's going to be the union of the intervals where the sign of the output matches the inequality symbol in the problem. So we need to look back here. Remember, this is what we said y is equal to. That just means we're looking for y less than 0. We see that y is less than 0 for any x in this interval and also for any x in this interval. The numbers in these intervals are solutions of the original inequality. Let's shade them on our number line. Also, step 5 says we're supposed to include the zeros of the function in the solution set if the inequality symbol is either greater than or equal to or less than or equal to. But our inequality is just less than, so we won't include the zeros in our answer. So the set of solutions is just these numbers right here. Writing this using interval notation, we have this as our answer. Take a look at the next problem. It's very similar to the one we just got done doing. So I'll let you try this. You can pause the video, try this, and then when you're ready, unpause it, and then I'll work it out. Okay, I'm going to go through this one a little more quickly because we've already done a very similar example. Step 1 is already done. We've got 0 on the right-hand side, and the left-hand side is a single fraction. Step 2 is treat the left-hand side as a function, and then find its domain and find its zeros. Since y is a rational function, we need to focus on its denominator. What numbers would cause us to divide by 0? So let's factor that denominator and see. We need a sum of -4 and a product of -5. So the numbers we're going to use are -5 and 1. Since the coefficient of x squared is just 1, we can factor this directly as x minus 5 times x plus 1. Thus, x can't be 5 or -1, which means the domain is all real numbers except for those two numbers. Now we need the zeros of this function. To find them using algebra, we put 0 in for y and we solve for x. Let's multiply each side of the equation by the denominator. We do this because we're solving an equation, and by multiplying each side of the equation by the same thing, we keep the equation in balance. So the left-hand side stays 0, 0 times anything is 0, and on the right-hand side we put the denominator over 1, because that doesn't change it, and it allows us to multiply these two fractions, and we can cancel this and this. So the right-hand side is just x squared plus x minus 6. At this point, we're solving a quadratic equation. Since we already have 0 on one side, we want to factor the other side. Here we're looking for a sum of 1 and a product of -6, so I'm going to use the numbers 3 and -2. This means that 0 is equal to the quantity x plus 3 times the quantity x minus 2. Using the zero product rule, we set each factor equal to 0, and then we get x equals -3 and x equals 2. So these are the zeros of the function. Now for step 3, we draw a number line, show the numbers that are not in the domain, -1 and 5, and we also show the zeros of the function, -3 and 2. These four numbers subdivide the number line up into 5 intervals, and here they are. We pick test inputs, we calculate outputs, and then we write down the sign of y. Note that if you chose different x's than I did, it's okay as long as your x's are in the interval. What's really important is the sign of the outputs. One other place to be careful is calculating the value of y. If you use the calculator, it's really important that you use it correctly so that the y's do correspond to the x's that you chose. So that was step 4. Step 5 is figuring out what our answer is going to be. Remember, we want y to be greater than or equal to 0. So first of all, where is y greater than 0? Well, in this interval, and this interval. And where is y equal to 0? Well, it's equal to 0 for the zeros of the function, the numbers -3 and 2. So let's shade these on the number line. Here are the numbers in these intervals, and then here are the zeros. So now all we need to do is to take the numbers on the number line and write them using interval notation. So we have 3 different intervals. They're going to need to be union together. And for the numbers that have the shaded dots, the filled in dots, that means we're going to need to use square brackets to indicate that those numbers are part of the set. So the first interval is from -infinity to -3. The next interval is from -1 to 2, and the last interval is from 5 to infinity. But we have round parentheses on the -1 and the 5, square brackets around the -3 and the 2, because they are solutions. If you have any question about this or the first problem, you can always email me. Now for the next page. There is a connection between the sign of a rational function's output and the vertical position of its graph. A function is called positive over some interval if its graph is above the x-axis for that interval, and a function's negative over an interval means its graph is below the x-axis for that interval. Wherever you have a zero of a function means that you can find an x-intercept on the x-axis. And this is new. A number not in the domain of a rational function means that the graph has a discontinuity for that value of x. The discontinuities are things like vertical asymptotes, and that's what we're likely to see. Example 3, part A, asks us to rewrite the equation of function g so the right-hand side is a single fraction. We'll do this by finding the LCD and using it to get a common denominator. The LCD is just the product of the two denominators, x times x plus 3, so we'll multiply the first fraction by 1 by x plus 3 divided by itself, and we'll multiply the second fraction by 1, which is x over x. That'll give both fractions the same denominator when we multiply. Notice that when I multiply the fractions in the numerator, I distribute, but I don't do so in the denominator because it's not necessary. Now we subtract the numerators and we get this. And that's the answer for part A. The last line in that rectangle tells us where g has discontinuities. It's just for numbers not in the domain. So what is the domain of g? Well, we can see x is not allowed to be 0 or -3. So those are also the numbers for which g has a discontinuity. Next, we're supposed to find the zeros of g, the inputs that make the output equal 0. So we'll take the output of g, set it equal to 0, and now solve for x. To do this, we'll multiply each side by the denominator. On the left-hand side, we can cancel the x's and the x plus 3's to give us 2x plus 12. And on the right-hand side, 0 times anything stays 0. Subtracting 12 from each side and then dividing each side by 2 gives us x equals -6. So this is the 0, the number -6. Now we're ready for part D. We want to use algebra to solve g of x less than or equal to 0. So if I take the output of g of x, that fraction, and then write down less than or equal to 0, this is a rational inequality that I need to solve. The first step is to get 0 on the right-hand side and a single fraction on the left-hand side. And that's exactly what we did in part A. Step 2 says we're supposed to treat the left-hand side as a function and then find its domain in zeros. But it already is a function. The left-hand side is our g, and we've already found the zeros and the domain back in parts B and C. So there's no need to do all that work again. So we're ready for step 3. I'll draw a number line, show the numbers not in the domain on that number line, and my 0, and then we'll use that to form intervals. Now we'll finish the interval chart. I'll pick test inputs, I'll calculate the outputs, and I'll find the sign of y. For the first interval, I need an input that's less than -6, so x equals -7 seems to make sense to choose. And for the second interval, I need a number between -6 and -3, perhaps x equals -4. And then for the third interval, something between -3 and 0, how about x equals -1? And then for the last interval, I need something bigger than 0, so I'll choose x equals 1. Now, the y values are the same thing as g of x, so I'm going to have to plug -7 into g, -4 into g, -1, and also 1 into g to find the outputs. These will be my y's. In each case, the sign of y is easy. Y is less than 0, y is greater than 0, y is less than 0, and y is greater than 0. To finish the problem, we need where y is less than or equal to 0. Well, y is less than 0 for this interval and for this interval, and y is equal to 0 for the 0 of the function, -6. So I'm going to shade these numbers on the number line, and then we can write our answer. The interval from negative infinity to negative 6 is these numbers, and then the interval from negative 3 to 0 is these numbers. Now we also need to fill in the number negative 6, so I'm going to put a filled in dot on negative 6. So the solution set is the union of these two intervals. It's the interval from negative infinity to negative 6 with a square bracket on the negative 6, union that with the interval from negative 3 to 0 with round parentheses around those. Okay, now we have just the last two parts. Where is the graph of g above the x-axis? Well, that just means where is g of x greater than 0? Where is y greater than 0? And we can see from our interval chart, it's just these two intervals. So here they are. We just list them. Notice, no more work needed to be done. The same thing is true for part F. To list the solution set of this inequality, we just need to recognize that the left-hand side is g of x. So we're just trying to solve g of x greater than or equal to 0, which means y greater than or equal to 0. And we've done all the work, all the previous steps. G of x is greater than 0 for the two intervals we found in part E, and g of x is equal to 0 for the 0, negative 6. So just put those together and we can write our answer. Since negative 6 is included in the answer, we put a square bracket around the negative 6 instead of a round parenthesis. So the solution set is this. And we're finished with lesson 21.